All right, well, hello, everybody. Sorry about the little technical hiccup we had there, and thank you very much for spending a little bit of your weekend time to learn a little bit about some robotics and what we can do with Arduino, and starting from the really basic level, looking at what the Arduino is and how it can get your wheels spinning, so to speak, and up to something new that I just discovered about controlling your robots wirelessly. So let's start the presentation here. So Arduino is going to be the foundation of our project here that we're going to work on today. And some of the things that I'm going to be going over are controlling servos and DC motors and what those are. How we can hack a standard servo for continuous rotation, which allows our wheels to rotate. How you can make what I think is probably the easiest, simplest robot you can put together. How you can use your 3D printer to make a couple of robot platforms that I've developed for you, and I host them up on Thingiverse. Some of the sensors that you can attach to your robot to give it a little bit of awareness in its surroundings, to have it respond to some of the things that it comes in contact with. And then finally, wireless control for your robot. It's probably about as inexpensive as you can get. It uses an old phone. Let your slide pop up. There we are. So welcome everybody. I love robots. So I've been playing with robots since I was a little kid, and I teach my students about robots. I bring robots home for my kids to play with, and they're just really exciting engineering devices that can inspire really anybody to want to learn more. And the heart of the robot, or the brain rather, that I typically turn to is the Arduino, because it's such an easy platform to begin. Turning motors, sensing information, and flashing lights, and doing all sorts of fun things. And really, you can find an Arduino in anything as simple as what we're going to work on today, which is just a two-wheeled robot, to relatively complex UAVs, which are unmanned aerial vehicles. One of the things that I teach at the high school is energy efficiency, and we look at these UAVs and how you can improve their battery and power consumption efficiency by using some complex algorithms for the flight path. And this is all based on Arduino, so it's a pretty exciting platform to start learning with. So what is Arduino? So those of us who've been playing with these for quite a while are relatively familiar. They come in all sorts of different shapes and sizes. And the Arduino isn't just a thing. It's actually a combination of a development environment, this program that you can write the software that gets uploaded onto the Arduino as firmware. Now, the different shapes and sizes typically take and leave different capabilities, where one would have more input and output capability than the other, but really they're all based around the same idea of having this open source platform for people to develop new and interesting things. So one of the questions my students always have when we start programming these microcontrollers is can you program it again? Is it like a CD-ROM where you burn it once and it always has a program on it? And yes, the neat thing about the Arduino platform is that it can be programmed over and over and over again. And so you can write your software on the computer, send it to the Arduino, and then tweak it and send it again and again until you get it the way that you would like. And this really aids when you're troubleshooting your programs and when you're working with the robots and sending commands and updating the platform. The other interesting fact is that the program remains on this Arduino after the power has been removed. So if you unplug the battery or the power source or the USB cable, it'll still be there when you power back on. So this is great when you program at work or at home and you want to bring your device or your robot to show somebody, and it'll be there when you turn it back on. Now, lastly, about the Arduino platform. So this microcontroller device has the capability of interfacing with the world around it, and it's done through really two main sources: the digital input and output lines, as well as the analog channel. Now, the digital are designed to communicate with with devices such as an SD card for storing data, or digital sensors, or to output in a digital format, which is in an on or an off state, so you could run things like an LCD, or just turn a light on or off, or even sense the position of a button. The analog inputs are more useful for platforms such as robotics, which is looking for feedback that's not necessarily just on or off, or high or low, or bright or not. It's actually looking for the analog, or the difference between those two. So I like to use a light switch as the example, where in a standard room you go and you flip the light on and the light turns on. You flip the light switch off and the light turns off. But some of us have dimmer switches, and so you can set the light intensity to just the way you want it. And an analog input works very similar to a dimmer, where the light can be all the way on or some of the way off, and the Arduino can sense the difference between those and give you a number that represents to that intensity. And so this is really useful when we talk about robotics, because you can sense whether you're getting close to something, or you can have thresholds that help the robot respond to the obstacles that it might come against. Now with robotics too, typically you're working with higher power devices like the motors or actuators or relays that you might have on your robot. And the Arduino platform is designed around, or rather there's a bunch of shields which are attachments to the Arduino that are designed around the capability of the microcontroller. So you can expand some of the digital input-output or analog channels to do better or bigger things. So a relay shield or a motor shield might be able to control larger motors using the same Arduino. That's the end of the introduction section. Please feel free to ask questions. I've got a little chat window in front of me here, and I can happy to answer any of the topical questions that you might have, and I've got time at the end of the presentation too that I can help answer some of your questions. Now moving on to controlling servos and DC motors, which are really the basis for which most robotic projects are focused on, where servos are ready-made motor gearbox devices, and DC motors can typically be found without gears, with gears, from scavenged parts and the like. So we'll talk about this. Now a servo, as I said before, is a combination of a DC motor, electrical components, and a gearbox. And on the side of the servo, you see a 3-wire connection, which is pretty standard to most servos. And these give both the power and the data connection to the servo itself. So the advantage of using servos like this in your robotic project is that they don't require any external circuitry. You can essentially hook it directly up to the Arduino and have it operate. Now, because it has a gearbox inside of it, it provides a relatively high torque with a low RPM output, which is good for things like robotics, because typically you're going to want to drive your robot over something other than a glass smooth surface. You'd like it to go over carpet or outside in the grass. So you need to have more torque, which is the turning or twisting force, the ability for your wheels to overcome the weight of the vehicle or the resistance against the vehicle. And the output on these is typically a low RPM, which makes for good control. Now the output RPM of servos can be increased by adding gears to the output of the servo. So if you take this relatively low RPM output and connect it to a relatively large gear, and then connect your wheels to a relatively small gear, the output would be amplified, or the RPM would be amplified, rather. Now, servos have a 3-wire connection that is mostly universal. The little black connector you see here is different for different manufacturers. They all feature the same 3 wires, though. Some of them have different colors, where the typical one I usually see is red, black, and white, or white, red, and black, as the order might go. But you might see orange, red, and brown, or you might see a couple different colors depending on the manufacturer. Now, these wires are designed to take both. Excuse me, I have a question coming in. Okay, I'll answer that in just a second. Now, you might use, with a 3-wire connection, you'll see that the red is always in the middle. Now, this positive voltage, where the positive voltage is attached to the servo, is put in the middle for a reason, where if you connect your servo backwards, you don't run the risk of damaging it. So by having it in the middle, you can plug it in one way, you can plug it in the other way to your say, receiver for the radio controller or to your robot, and it won't damage your electronics. Now, because data is sent over the one outer wire and ground is sent over the other outer wire, it doesn't matter if those get mixed up. All you have to do is unplug it, turn it around, and the system should work again. Now, the last thing I'll note about this 3-wire connection is that servos are designed to operate up to about 7.2 volts. Now, the Arduino itself typically runs at 5 volts. You can put a larger voltage source into it, like from a wall wart or a battery pack, and it has an onboard voltage regulator that brings that voltage down to 5 volts. Now, if you were to, say, put over 7.2 volts into the servo, it runs the risk of burning out some of the internal electronics. So I usually try to keep it around 5 volts. You can get a little faster RPM if you go to a higher voltage, but 5 is typically the standard for servos. Now, there are 2 different types of servos. There are analog and digital, and it pertains to the method in which data is sent to the servo. Digital servos are typically more stable. They don't tend to oscillate as much as analog servos do, but they are more expensive and a little harder to find. Most servos that you'll find at the hobby store or Radio Shack or online are going to be analog servos, and they operate like this. Now, if you look at the graphic on the right of the slide, there are 3 little square waves, and this illustrates what's called pulse width modulation, or the frequency at which you send a pulse to the servo. Servos like to see a pulse every 20 milliseconds or so, and the length of the pulse, or the width of the pulse, tells the servo what position to sweep to. Now, this is really handy when you're working with something like a robotic arm or an actuator or some sort of device that requires precision in the position of that servo. In the case of us, we're working with robots which have wheels that are rotating. So this pulse width modulation is actually going to tell the servo what direction to rotate. So the top, most servos start at 1 millisecond or 1,000 microseconds. It's going to put the servo into the 0-degree position. 1.5 milliseconds or halfway to the 2 millisecond point would put the servo halfway through its rotation. And then at 2 milliseconds, it'll put the servo at 180 degrees. Now, digital servos typically have a 90-degree rotation, which is important to note because when you're working with things like actuators and manipulators and any sort of servo use that requires that position, digital servos only rotate to about 90 degrees. So you actually get more rotation out of the analog servo. Now, looking at Arduino as this platform for designing our robots or controlling our robots, there is a lot of libraries built into the Arduino that allow for control of things like servos to be simplified. But without using a library, you can have the Arduino output a specific pulse that the servo can understand. And in the program that I've written on the side, it's just as simple as it can be to control 2 servos to just twitch. And all we're looking for is that the connection is appropriately made to your Arduino to control those servos for future application. So at the beginning of the program, we just initialize those 2 pins, pin 11 and 12. And there's a reason we're using 11 and 12, and I'll explain that as we look more into building our robots here. But we initialize them as output pins. Then we get to our loop where we set those output pins high for 1 millisecond, and then we set them low indefinitely, and we have our Arduino stop with a while 1 command. And all that's going to do is send one pulse, one millisecond pulse to the servo, and it'll make it just twitch once. That's all we're looking for. Now, if we would like our servos to actually rotate, we can use the servo library. And the program that I've illustrated here imports the servo library, which takes over all of the lower level control of the servos and attaches them to timers inside of the Arduino, and makes for a lot easier control of our robot. So again, in our setup, we attach a servo to pin 11, and we're only controlling one servo with this program. We get to our loop, and we have two for loops which attempt to make our servo sweep from one side to the other side. So in the first loop, we write 180 degrees or 180 to our servo, and we delay for 15 milliseconds, which lets the servo get to that point, and we loop that 100 times. For the next for loop, we do the same thing where we loop 100 times, but this time we write the 0 to our servo, and it would sweep it back to the other side. And this program continues indefinitely. So if we were to upload this program to our Arduino, and we have our servo connected to pin 11 and our 5 volts attached to the servo, it should sweep back and forth. Now, the standard Arduino Uno is capable of controlling up to 12 servos, which is a significant amount. You can do a lot with just those 12, make a robotic hand or a walking robot. But if more are needed, you can go to a larger microcontroller like the Arduino Mega, which has the ability to control up to 48 servos, which is an impressive amount. Now, let's see. The next type of rotational device that we're going to work with is the DC motor, which is the easiest to come by and the least expensive. Now, DC motors don't necessarily run at the voltage that our microcontroller run at, so we need to add some additional components in order for this motor to be controlled by the Arduino. Now, they typically require gearing in order to operate at lower voltages, just due to the nature of the motor. Some motors are capable of running at low voltages for what the Arduino is operating at, but won't have the power enough to make our robot move. So you need to add a gearbox, and there are geared DC motors, which is what we're going to use in one of our 3D printed robots. Now, in order to make these motors turn, there's two simple ways of doing so. The first is with a transistor, which allows the motors to rotate in one direction, and there's an H-bridge, which allows the motors to rotate in both directions, both clockwise and counterclockwise. So if we look at the simple schematic here for attaching a transistor to our DC motor, this transistor that I have illustrated is a TIP 120, and if you went to, say, Radio Shack or Mauser or really any electronics distributor, a Darlington transistor like the TIP 120 is pretty standard fare. The way that it would attach to the motor is by connecting the input of our Arduino here to a 1 kilo ohm resistor. And on the output of this, and actually it looks like I've attached my motor to the wrong pin here, I'll have to update the graphic. The black line on the motor actually attaches to the diode, which is the black with the white stripe component. But the idea here is that the Arduino inputs a pulse width or a pulse signal to the transistor, and it turns on and off the output of the motor. And the speed of this can be controlled with pulse width modulation. I'll talk about that in the next slide. Got a couple questions coming in here, and I will begin to answer some of them at the end of this section. So looking at changing the speed of our motor, and I talked briefly about analog input or reading analog signals into the Arduino. We're capable of generating analog output, or it's a simulated analog output in the form of pulse width modulation. The pulse width modulation is the speed at which the Arduino can turn on and off a 5-volt source. So the example that I like to give my students when we're talking about PWM is if you look at a Macintosh, or excuse me, an Apple computer, and they always have a power light that slowly gets brighter and then slowly gets dimmer. Now, they're operating that LED at the same voltage, but what they're doing is that they're turning that LED on and off fast enough that you see, or it sees, a lessened voltage and makes it dimmer. So the Arduino is capable of doing this as well using the analog write command. And depending on the number that you send through the analog write command, tells the Arduino how fast to turn on and off that output. Now this is applicable to controlling our DC motors because we can change the speed at which it rotates. Now if you have ever used a radio-controlled vehicle and you want to make it go slow, typically you can actually hear this PWM, and it's kind of a whining, slightly high-pitched screeching noise that emits from the motor when the motor is spinning slow. And that's the sound of the armature actually energizing at the frequency in which the analog right is operating at, and you can hear that pulse width modulation frequency. So it's really nice that you have the ability to change the speed at which your motors are turning, not just have them turn on or turn off and your robot go out of control. So it adds another layer of control to your robot. Now the easiest way to get bidirectional, or the ability to turn the motors in both directions on the Arduino, is to use an H-bridge like the L293D. Now this is another very standard component that anybody can pick up at Radio Shack or online at Make or Adafruit or wherever. But the L293D is a series of these Darlington transistors, like the single transistor configuration we had before. But instead it has digital control lines which allow you to change the polarity or the connection of positive and negative voltage to your motor. And looking at this graphic looks a little confusing, but when it's attached to the motor and the Arduino, it all makes sense. The pink lines here are the activator, the enable lines for each of the motor channels, and there's 4 motor channels here. So hypothetically, you could connect 4 motors to the L293D and have them all spin in the same direction. But in our case, we'd like to control just 2 motors and have them both spin clockwise and counterclockwise. So in the configuration I have here on the little breadboard, the 293D is connected to the Arduino using all of the pink lines, the enable line, and the 5-volt DC line, and the ground. The rest of them, M1A, M1B, M2A, and M2B, illustrate the wires that are connected to the motors. Now when the enable is pulled high, so it's turned on, and E1A would be turned on, the motor M1 would turn on. Now if E1A were turned off and E1B were turned on, the same motor would turn on but rotate in the other direction. So in order to kind of simplify this confusing explanation of how the 293D works, I've written you a program which is a little bit longer than what I could fit on the slide, so I've linked to it here to my Google Drive. You're more than welcome to download and then get an idea of how you can control your geared DC robot using the Arduino with only four of these control pins. No, I think I might save these questions to the end. That'll just help with continuity here. So our next section is going to be talking about hacking servos. Now, not all of us are going to be able to find continuous rotation servos or servos that will just continue to rotate. Most of us will be able to find standard servos, whether it be from an old project or we go to the hobby store, or we just find them in the garage, which is what I tend to do. Let's see. So what this project here is going to look at is setting up a standard servo that you might have from an old project or the like, and allow it to rotate continuously, which gives you a geared DC motor that's controlled with a digital line to the Arduino in one little box. So it's a very easy to use, nifty device for giving your robot motion. Now, as I said before, servos are designed to rotate and hold position to that specific degree, that specific angle that we give them. If we want to modify this, or we want to hack our servos to rotate continuously, it requires only 2 little modifications to the inside of the servo, which makes for a fun little project. So in order to complete this project, I always start everything off with safety glasses and a couple standard components in order to take the servos apart. I will note that I require soldering iron and solder because there's an electrical connection that needs to be altered. And the only semi-unique components that you might need are 2 10 kilo ohm resistors. Now the resistor values don't particularly matter as long as they're over, say, 5 kilo ohms, but they need to be matched. The way that the servo works is that it has a potentiometer inside that we'll see later that tells the servo what the position is. And so we're going to trick the servo into thinking that it's in its middle position by using these two 10 kilo ohm resistors. And then a little heat shrink tubing or tape. I like heat shrink because it tends to last longer than, say, electrical tape. Now, the first step for hacking a servo is to take it apart. And this is usually done by using a small Phillips screwdriver, and there's 4 screws at the bottom of the servo that hold the casing together. And the casing usually consists of 3 components, a plate on the bottom of the servo and a cap on the top of the servo that protects the gears. And you want to carefully remove the gears. I like to take a photo of things before I take them apart because it helps with reassembly. But there's only about 4 gears that go inside of the servo that make it operate. Now, the first gear, the largest one that actually protrudes out of the servo, or the output gear, is the one that prevents the servo from rotating more than that 180-degree sweep. On that gear, you can see a little red tab that I've highlighted with a Sharpie. And that tab is a mechanical stop that actually prevents that output from rotating past that 180-degree mark. So the first thing we're going to do in hacking our servos is remove that tab. So you carefully use your hobby knife to remove the tab and make sure you trim away as much of it as possible because that point will now sweep underneath another gear. So this will allow our servo to rotate 360 degrees and on. The next step is to take apart the bottom of the servo, and you do so by slowly or gently pulling away the little circuit board that connects the input from your microcontroller to the motor and the controller. And you see that there are 3 little wires that connect to the potentiometer. Now, a potentiometer is just an analog or an adjustable resistor. And this is just like our dimmer switch on our light, where you can change the brightness of the light. A potentiometer can change the resistance by sweeping from left to right. We can trick our servo to think that it's always in its middle position by disconnecting those 3 wires and attaching them to a pair of resistors. So we take our 2 10 kilo ohm resistors and we twist them together so that we now have a resistor pair with 3 legs. And we're going to solder those 3 wires, that red, yellow, and green, to that resistor pair. And if we take those 3 resistors and we solder them on, and here you can see the green is on the top, yellow is in the middle, and red is on the bottom. Isolate everything with a little bit of heat shrink, and then you can stuff it back into the servo. Now, some servos rely on the potentiometer for support of the output gear. The way that you can get around this is to actually take the potentiometer apart and remove the components from the inside. This will allow the output gear to still have the support structure to rotate, but it won't have any feedback from that potentiometer. Alternatively, you don't even need to have the potentiometer inside of the servo since you've replaced it with the pair of resistors. So we reassemble our servo, and here you can see the 4 gears stacked in order, and your servo should be ready for continuous rotation. Now, one of the things my students love to do is to take, and if there's something attached to the output of the servo, like a servo horn, they love to sit there and twist the servo back and forth because it makes a satisfying gear rotating noise. But the problem with doing this is that the gears inside of the servo are made out of plastic, and that gear satisfying rotating noise is the result of the gears interacting with each other and spinning relatively fast. So it's not a good idea to do this because you run the risk of stripping or removing the teeth off of the gears. So that's something you certainly don't want to do. Now this brings us to the world's simplest Arduino robot. And this is my idea I had a couple weeks ago for developing a platform for robotics for really anybody to do. And it starts with the purchase of an Arduino. Now, I'm no Arduino salesman. I have no interest in being one. But purchasing an Arduino that comes in a box is what forms the platform for this robot. And so I've purchased just the standard issue Arduino Uno here. and it comes in this nifty little cardboard box. Now, by using that box as a platform, we can attach all of our components to it and actually make a robot out of it. I just noticed that the text on that slide is incorrect, so I'll have to update that for you all. Now, in order to complete this robot, you need your hobby knife and a couple of components, but no soldering iron or anything technical like that. For the materials, we're going to use CDs as wheels. We need a pair of continuous rotation servos or ones that you've hacked. We need a 9-volt battery with a battery clip that has a barrel jack on the end. We need a large paper clip, some heat shrink tubing, and some double-sided tape. Now you start this project off by removing the Arduino from the box and try to keep it as intact as possible. And position one of the servos opposite of the side that you opened, and so that one of the mounting tabs on the servo goes just to the end of the box. And then mark these two positions with a pen, and that's going to make the, or give you the marking for the cutout for the servos. And so use a hobby knife to cut out those rectangular shapes, and you should be able to slide the servo straight into the box. Now secure the servo in place with 2 pieces of double-sided tape, and repeat for the other side, and your servos will be mounted. Now, the nice thing about this setup is that there's enough room on the other side of the box to house a 9-volt battery, making this a pretty nice little platform for making a robot. The next thing we're going to do is take the standard servo connector, that 3-wire connector, and we're actually going to remove the wires from inside of the connector. This is going to allow us to connect these servos directly to the Arduino without having to use a shield or do any soldering. Now, one of the things that in my opinion, is missing from the Arduino platform is a standard servo connector. Because it's used in so many robotics projects, it makes for an easy addition. But with the project that we're using today, we're using a standard Arduino Uno, and it's going to not have these standard 3-wire connections for our servos. So we're actually going to take advantage of 2 connectors that exist on the Arduino that we'll talk about in just a second. The way you remove these wires is to carefully slide your hobby knife underneath the little black tabs that hold those wire connectors in place. Now these, after they're lifted up, the wires slide straight out, and you want to insulate them with a little bit of heat shrink or just one wrap of electrical tape. Now the first servo is actually going to connect to what's called the ISP header, or the in-system programming port. Now on the Arduino Uno, there are 2 of these. The USB to serial converter actually has an ISP, and the Arduino itself, the AVR, has an ISP. Now these ISPs are connected to both power and pins on each of these microcontrollers. Now because there are no male pins on the Arduino that are designed for this, we have to take advantage of the ISP. So with one servo, we're going to connect it to only the power at the ISP to the USB to serial converter, and that's what's illustrated here. Or you're going to connect the red wire to pin 2 and the black wire to pin 6. Now the pin designation is illustrated with a little white dot next to the ISP, and the graphic that I've shown you here tells you which pin connects to where. So pin 2 to 5 volts, pin 6 ground. Now for our other servo, we're going to use the Arduino's ISP, where we're actually going to take advantage of the fact that there are 3 digital I/O connected to this port. One of those is connected to the LED, which is pin 13, and all Arduinos have a pin 13 LED, which is used for visual feedback. So we're going to take advantage of the other 2, which is Arduino pin 11 and Arduino pin 12. So we're going to take the remaining 4 wires, the control wire for the first servo and the power and control wire for the second servo, and connect them to this ISP. So our remaining red and black wires, red will go to pin 2, black will go to pin 6, and the remaining white wires will go to pin 1 and 4. And now we've made a direct connection from our servos to our Arduino without doing any soldering. We attach the Arduino to the top of the box with a little bit of double-sided tape. And you can see the pigtail from our battery coming out of the back of this. And then connect your servo horns, which is this white 4-pedaled horn that connects the servo to our wheel. And you connect them using 4 little pieces of double-sided tape and press the CD on as centered as you can to that servo horn. Now we're going to make the third wheel, or the dragger for this robot, using just a simple paper clip. So if you unbend a large paper clip and tape it to the bottom of your box, as shown, it'll allow the robot to balance. And finally, your robot should look like this, where you have the 2 wheels attached to the servo, the Arduino on top, and everything working together to make for a very simple robot platform. And as we discussed before, we're going to use the servo library. So using this simple code, where we initialize the servo library and pins 11 and 12 as servos, the robot should rotate forward. Now, the only thing to illustrate in this program that's a little different is with the left servo, we're going to rotate it counterclockwise, or at 180, and the right servo, we're going to rotate to the opposite. Now, because the servos are positioned opposite of each other, you want them to rotate in opposite directions so that when they're on the robot moves forward. If we wanted to rotate, we can make both the outputs 180, or we can make them both 0, and the robot would turn to the left or turn to the right. And if you inverse their output, where the left servo would be 0 and the right would be 180, the robot would reverse direction. So you have full control of the motion of the servo or motion of the robot by changing the direction of the rotation of the servos. Now, I'm a big fan of 3D printing, and I use it heavily in the classroom. And so I developed 2 chassis, or robot chassis, that rely on the 3D printer alone to produce a robot for you. So the 2 links that you see here, and they're under your URL section on your window, bring you to 2 projects that I put together for making a very simple robot for the Arduino. The parts and materials that you would need are essentially the same for the other projects, except you need a 3D printer and some 440 hardware. Now, this illustrates the size of the nuts and the bolts. So if you went to a place like Home Depot or your local hardware store, you should be able to find these components. The last material that you'll need is a glass marble, which acts as the dragger or the tail wheel for this robot. After you've 3D printed the robots that you would like to use, whether it would be the gear-based robot, which is this, which uses a Tamiya gearbox that's illustrated on the Thingiverse page, or you would like to use one with servos, you go ahead and print them out on the 3D printer and begin assembly. Now, it's only 3 pieces with 2 wheels which attach directly to the gearbox, and the body of the robot which connects the gearbox to the Arduino. For the servo robot, looks like this on the right, essentially the same as the gearbox, except it uses the continuous rotation servos. And you attach them using the screws that are provided with the servos. And lastly, you need to connect the control circuitry. Whether you're using a gearbox, you would be using an H-bridge to make the robot operate. And on a previous slide, I actually have a picture of one of these robots set up with an H-bridge, or with the servos, connect them in the way that we did with the previous Arduino Box robot. So by now we should have a very functional robot platform that can move forward, back, left, and right, but it doesn't really have any ability of interacting with its environment. And that brings us to the sensors. Now, sensors are going to provide feedback to your robot that allow it to determine whether there's an obstacle in front of it, or something is a distance away, or say you want your robot to follow the sun. You can use sensors to help your Arduino determine the variables that you would like. Now, the 2 types of sensors that we're going to talk about are touch sensors and acoustic sensors. Touch sensors are the simplest form of sensor that we're going to be using, which is essentially just a switch to turn on and off. And an acoustic sensor is it going to give us that analog or that ability to sense the distance an object is away from us. So with a touch sensor, are typically attached to a robot using antenna-like extensions from the switch. And all it is a standard switch connected to one of the digital inputs on our Arduino. The switch is connected using a resistor and a little bit of wire. And in order for the Arduino to determine whether the switch is pressed or not, the resistor acts as what's called a pull down, or it sets the initial state of the switch or the input as 0. So in the case of our schematic here, if the switch were not pressed, the Arduino would see a 0. If the switch were pressed, the Arduino would see a 1. And so we can write a program that says, if the switch is pressed, then stop the robot and say back up and turn a little bit and try again. And so by adding some very simple control commands to our robot using 2 or more switches, we can actually give it a sense of the world around us and have it not crash and stop as it goes down the hall. Acoustic sensors are more expensive than standard switches, which can be found in most junk electronics. Acoustic sensors use a very similar to an echo or echolocation like a bat uses, where it sends out a pulse and it waits, and then it receives the echo of the pulse, and it determines the distance an object is away from the sensor by measuring the time delay between the send and receive of that pulse. Now this device can be attached to the front and sides of your robot, allowing it to know where it is relative to the world around it. So rather than going until it bumps into something, it can avoid obstacles without making contact. 2 of the standard acoustic sensors are the SRF04, which uses a PWM output, and an SRF10, which uses a digital I2C output, both requiring 2 Arduino pins, but makes it a little easier to control, in my opinion, when you're using I2C. But both accomplish the same. Now the last project I'm going to talk about, which is the one I just finished working on and quite excited about, is the ability to control your robot wirelessly from, honestly, anywhere in the world that has an internet connection. So the way that I accomplish this is by using Google Hangout to feed the audio and video from a smartphone, and this is my old Android phone on the robot here. I've written a program that runs on the Arduino, which is based on a demonstration program, and the computer program which I wrote in processing to output TTMF codes over the Google Hangout audio channel. In order to construct this project, it requires just a couple of electronic components and some minor soldering. To note, you need an old an 1/8" stereo jack or an old pair of headphones to plug into your old smartphone, a couple of resistors, and a capacitor. Now to start this project, I work with the 1/8" stereo jack, which has left channel audio, right channel audio, and ground. I typically get mine from old headphones because they're readily available, but these can be found as just a bare connector from your standard or your local electronics distributor. If you're using an old pair of headphones, they typically have enamel-coated wire to carry the audio. The problem with enamel-coated wire is that it's very difficult to solder, and the way you do so is by isolating the 3 wires, the green, the red, and the black, or the silver, which it is typically, and you heat them with a lighter until they're red hot. By doing so, you burn off the enamel coating, and it allows you to tin and then solder those wires. The circuit is quite simple and is essentially just a filter and brings the voltage of the audio so that it swings from 2.5 volts at the middle up to 5 and down to ground. This allows for us to get a full range of audio input to the Arduino, and with the high-pass filter to get rid of any of the audio that we don't want to hear. I like to solder these components onto a small circuit board because they're very small to begin with, and then cover the entire circuit with heat shrink. Now on my circuit board here on the left is the audio cable coming into the circuit and 3 wires coming out of the circuit. One is our ground, power, and the audio that goes into our audio or our analog channel. Next, you're going to attach your phone to your robot and plug the audio cable in. Program your robot with the DTMF program that I've given you, and open up Google Hangout on your computer. Now, I like to use 2 different Google accounts, one for my computer and the other for the phone. That way that I can have a Hangout with myself. Now, open up the DTMF bot program on your computer, which is essentially just an audio player for these DTMF tones, where W gives us forward, A gives us left, S gives us backward, and D gives us right. Standard WASD configuration on your keyboard. So this allows us to control our robot by pressing these keys, therefore generating audio tones that get sent over the Google Hangout audio channel to our phone. Our phone picks up the audio, sends it to the Arduino, and the Arduino interprets the DTMF tones as commands to make your robot move. That way we get both audio and video to our phone through the internet. The next step is to turn the volume down on your computer after you verify that the DTMF bot program works, and plug a patch cable from your line in to your headphone jack. Now, some computers do this via software, but essentially we're trying to take the audio generated from the DTMF bot program on your computer and output it through your speakers, so that, output it through the line in, so that Google Hangout sees it as audio and therefore sends it to your robot. I have had success taking a pair of headphones and putting it over the microphone port on your computer, and have had it been able to control the robot that way. So if you don't have a computer that has both line in and headphone, it's still you have the ability to control your robot. Now lastly, you open up Hangout. Well, Hangout should be open on your computer. You highlight the DTMF bot program so you can still see Hangout. And with your robot on and connected to Hangout, if you press the W key or the ASD, your robot should move. As I said before, it takes a DTMF tone using publicly available DTMF decoding library and converts that into a command to make our servos move. This allows us to control our robot from essentially anywhere in the world, get video feedback using Google Hangout. So that's it for the day as far as my presentation goes. And we have a little bit of time now, about 6 minutes, that I can begin answering some questions. So thank you all very much for this first weekend webcast of my weekend robotics program here. So let's see, let's take a look at some questions.
Great presentation, Adam. Thank you so very much. Are you able to see the questions, or shall I read them out loud for you?
No, I've got them here. Thank you.
Great. And folks, we are at Q&A now. If you do have a question for Adam and what he's been talking to you about and showing you, open your group chat widget, type it in, send it in, and we'll take as many as we have time for. Back to you, Adam.
Right. Great. So the first question was, would you use Arduino to teach electricity and electronics to students, and any recommended courses for lessons? Well, yes, absolutely, and we do every day. We actually start our freshmen off with the Pickaxe microcontroller, which uses BASIC, but now we're actually moving on to the Arduino platform. Excuse me one second. The nice thing about using a microcontroller to teach electronics and electricity is that it gives you a very easy visual feedback from the operation of the electronic components. So we actually start off our teaching electricity and electronics with basic components like LEDs and resistors and transistors, and move up to the microcontroller, which has the same functionality, but doesn't use those discrete components. The next question is, my servos seem to move only over around 330 degrees. Is that a typical problem? Now, if you're in the middle of hacking your own servos to make them continuous rotation, what would prevent them from moving that full 360 degrees is if you still had mechanical interface inside or a mechanical blockage inside of your servo. So I'd recommend taking your servo apart, make sure the potentiometer isn't preventing it from rotating, as well as making sure that you've trimmed away any of the plastic that's on that output gear. The next question is a recommendation of whether you use a digital or an analog servo, and which is easier to control or more adaptable. Personally, I would recommend an analog servo, even though they're a little more jittery, which means they tend to get erroneous signals, which make them shake a little bit periodically. But most of the time, they're stable enough for the projects that I work with. Digital servos are a little more complex as far as the control circuitry they have, and they cost more. So if you're looking to hack your own servo, I would recommend an analog servo. All right, our next question is related to the twitch I just mentioned. And it says, the twitch means turn and then go back to the initial position, or does it stay in the turn position unless you send another signal? What I mean by that is it tends to jitter or shake, which would mean it would go from one position to the next, but over a very, very short distance, so maybe a half a degree. Now, with the program that I've illustrated before, I think it was the first servo control program where we only send it one pulse, the servo isn't going to have enough time to get from the position that it's in initially to that desired position. Servos hold position by sending that series of pulses or commands to the servo over a 20 millisecond period. So as long as that pulse of, say, 1 millisecond is repeated every 20 milliseconds, the servo will move to and then hold position. Otherwise, the servo doesn't have time to get to that position and typically shakes. Next question is, how do stepper motors differ from servos? They differ greatly in that there are two different motor types. Servos are DC motors that are positioned through feedback with the potentiometer. Industrial servos have different kinds of encoders, but for our hobby case, it's just a potentiometer. Stepper motors are capable of positioning themselves through control, but have the ability to rotate 360 degrees. They're used in things like the 3D printers, and any other scenario where you would need precise control over a continuous rotation. Let's see. Question is the point of hacking a servo to get a geared DC motor? Alternative is to buy a geared motor or create your own gearing system. And yes, the point of that is that producing a geared motor requires either mechanical design or the purchase of a geared motor system. With the two robots that I've illustrated, where one uses a gear box, which is made by Tamiya, everything's already integrated. But for the most part, if you were to harvest out of old equipment a DC motor, it's going to have a motor without a gearbox that would be useful for you for this robot application. So by using a servo as a geared DC motor, you have kind of the best of both worlds. You have the control circuitry, the gearing, and the motor all in one package. Great. Another was a response to that question on the geared DC motor. And would Lego gearing be a good option? And absolutely. Excuse me one second. With the standard DC motors, I think with the Lego systems, they actually have servos which are for continuous rotation. But if we're using Legos with just a DC motor, the gears with the, I think the Lego Technic and the Mindstorms are perfectly good for setting up a DC motor gearbox for your robot. it gives you both the structural alignment and the componentry and the axles to make it easy to do. The next question is about ISP. The ISP is the in-system programming port for the Arduino, and it's a port that's used to program the Arduino with its initial bootloader. The bootloader is what allows us to program the Arduino over USB and subsequently serial. Without the bootloader, you would need a special piece of hardware to program the Arduino. Now, you can buy Arduinos or just the microcontroller, which is pre-programmed with the bootloader, or you can program your own using an ISP programmer. Now, all of these Arduinos have these ports on them, and they're connected to pins that can be useful for robotics. They give us voltage output as well as direct connections to the different or 3 different I/O on the Arduino that give us the ability to connect 2 servos and something else, or 3 servos, or however many you would like. It just makes for an easy option for setting up a robot without doing any soldering. Let's see. The next question is, are the 3D files available to make this? And absolutely, all of the 3-dimensional CAD that I do, I put up on Thingiverse. That's THINGIVERSE.com. And if you search for my username, which is Adam Kemp, ATOMKEMP, you can find all of my projects there. The 2 that are linked here, and you should find them under your URL section, link directly to both the servo robot and the gearbox-based robot, which you are free to download and build. And the last question is Google Hangout for Android only or iOS? I use Android only, so I can't speak to whether or not iOS is the case, but you know what, I'll look it up for you. It appears that Google Hangout is on App Store, but don't take my word for it. I would search to Google just to make sure that it does indeed work on iOS. But the principle is the same. You're transferring the data to control your robot over the audio channel, so it should be platform independent. That is the last question. So I thank you all very much for taking part in this hour-long lecture on weekend robotics and how you can use your Arduino to make some very capable robot platforms. Thank you.
Excellent webcast today, Adam. Thank you so much for joining us and for spending time and for sharing all your knowledge and expertise.
You're very welcome. That was fun. I'm glad that my phone didn't explode again.
Folks that attended today, we thank you for attending our event. And yes, this was our very first Saturday event, so we thank all of you for joining us. And again, we had many people from all over the world, and for a lot of you it's very late, or even some of you very early there in Australia, so thank you so much. And for those that sent in questions, thank you for those, because having your questions really adds just so much more to our event, so we do appreciate it. As we wrap up, we'd like to let you know that we did push out a little code to you all as a thank you for attending our webcast today. So if you didn't open your group chat, open it now. There's a little code in there to save you some money on Adam's book, The Makerspace Workbench. If you like what you heard and saw today, the book has so many more projects and tips for you, so we do invite you and encourage you to take advantage of that discount code and get the book today. Thank you again, Adam. Thank you, everyone. This will conclude today's webcast. Goodbye, everybody.